Series solution of Bessels differential equation leading to Bessel functions. Most of the applied problems gives rise to the linear differential equations but of variable coefficients. Such differential equation cannot give us the general solution as a functions. However, we can obtain the solution of such differential equation by the numerical methods, or sometimes we can obtain the solutions of such differential equations as a convergent infinite series. The Bessel's differential equation of order n is in the form of x square d square y by dx square plus x dy by dx plus x square minus n square into bracket y equal to 0. Assuming the solution of the given differential equation to be an infinite series of the kind, say y equal to summation from r equal to 0 to infinity ar x raised to k plus r, or it can be written as y equal to x raised to k into bracket a naught plus a1x plus a2x square plus so on, just by putting r equal to 0, 1, 2, 3 etc. Then differentiate this y with respect to x, we get dy by dx equal to differentiation of this ar x raised to k plus r is ar into k plus r into x raised to k plus r minus 1, and again differentiate dy by dx gives us d square y by dx square equal to summation from r equal to 0 to infinity ar into k plus r into the differentiation of x raised to k plus r minus 1 is k plus r minus 1 into x raised to k plus r minus 2. Then substitute these dy by dx and d square y by dx square in the given Bessel's differential equation, gives us x square into d square y by dx square means it is a summation of r equal to 0 to infinity ar into k plus r into k plus r minus 1 into x raised to k plus r minus 2 plus x into dy by dx is summation from r equal to 0 to infinity ar into k plus r into x raised to k plus r minus 1 plus x square minus n square into y means it is a summation from r equal to 0 to infinity ar into x raised to k plus r equal to 0. Then take this x square inside, so that summation r equal to 0 to infinity ar into k plus r into k plus r minus 1 into x raised to k plus r minus 2 into x square, it becomes x raised to k plus r plus summation from r equal to 0 to infinity ar into k plus r into x into x raised to k plus r minus 1 is x raised to k plus r plus, just by expanding this bracket we get summation from r equal to 0 to infinity ar into x raised to k plus r plus 2 minus n square into this summation r equal to 0 to infinity ar into x raised to k plus r equal to 0. Now we can simplify by collecting the term containing x raised to k plus r. There were 3 terms are there containing x raised to k plus r. Those are summation from r equal to 0 to infinity ar into x raised to k plus r into bracket k plus r into k plus r minus 1 plus from the second term it is k plus r, then from the last term it is minus n square plus the remaining term is summation from r equal to 0 to infinity ar into x raised to k plus r plus 2 equal to 0. Then we can simplify it further by taking k plus r as a common factor between these two, that is summation from r equal to 0 to infinity ar into x raised to k plus r into bracket k plus r into k plus r minus 1 plus 1 minus n square plus the remaining term as it is, or here plus 1 minus 1 cancels, remaining is summation from r equal to 0 to infinity ar into x raised to k plus r into bracket k plus r into k plus r is k plus r whole square minus n square plus the remaining term as it is. Now we need equating to 0 the total coefficient of the lowest power of x, that is of x raised to k. This lowest power of x is obtained by setting r equal to 0. If we are setting r equal to 0 here, we get a naught into bracket k square minus n square equal to 0. That is setting a naught not equal to 0, so that we will have k square minus n square equal to 0 or k equal to plus or minus n. Similarly, equating to 0 the total coefficient of next lowest power of x, that is of x raised to k plus 1, that is obtained by setting r equal to 1. If you are putting r equal to 1, so that you will get x raised to k plus 1 term here, that is its coefficient is a1 into bracket k plus 1 whole square minus n square equal to 0. Or here this implies that either a1 equal to 0 or k plus 1 whole square minus n square equal to 0, or that is k plus 1 whole square equal to n square, or k plus 1 equal to plus or minus n, which cannot be accepted because already we will have a k equal to plus or minus n. Next, equating to 0 the total coefficient of x raised to k plus r. That x raised to k plus r term is obtained by here in the second term by putting r equal to minus 2. Whereas in the first term already we will have x raised to k plus r. So, one coefficient of x raised to k plus r is ar into x raised to k, ar into bracket k plus r whole square minus n square, plus from the second term the coefficient of x raised to k plus r can be obtained by setting r equal to r minus 2, that is ar minus 2 equal to 0. Or we can write ar equal to minus of ar minus 2 divided by k plus r whole square minus n square. Now, when n k equal to 1, that is my ar equal to minus ar minus 2 divided by n plus r whole square minus n square, or it is minus ar minus 2 divided by 2nr plus r square. Then putting r equal to 2, 3, 4 etc. we get when r equal to 2, a2 equal to minus a0 divided by, when r is 2 then it is 2 to the 4n plus r square is 4. Then when n equal to 3, r equal to 3 we get a3 equal to, that is minus a3 minus 2, it is a1 divided by 2n into r is 3, that is 2 3 6 n plus r square is 3 square, that is 9. But found to be a1 is already 0, this is equal to 0. Therefore, a5 equal to a7 equal to a9 equal to etc. equal to 0, because we are expressing that all these a5, a7, a9 etc. in terms of a1, hence all these becomes 0. Now, when r equal to 4, we get a4 equal to, that is minus a2 divided by, when r equal to 4 it is 2 4 8n plus r equal to 4 it is 16. Similarly, we can obtain a6 etc., a8 etc. Yes, by the substitution of that a2 value, we get a4 equal to minus 1 divided by 8n plus 16 into minus a0 divided by 4n plus 4, or minus into minus is plus a0 into, between these two 8 is common, here between these two 4 is common, 8 4 is 32 into bracket, here n plus 1 into bracket n plus 2. Like this way we can obtain the values of a6, a8 etc. Substituting the values of all these a0, a2, a4, a3 etc. pair into the equation 2, that is y equal to x raised to k into bracket a0 plus a1x plus a2x square plus so on, with k equal to n, we get the first solution as a y1 equal to x raised to n into bracket a0 plus, and a1 is found to be already 0, then a2 equal to minus a0 divided by 4n plus 4 plus a3 is 0, then a4 is a0 divided by 32 into bracket n plus 1 into n plus 2 into x raised to 4 plus so on. Or we can take out a0 common, the remaining is a0 into x raised to n into bracket 1 minus x square divided by, between these two we can take out 4 is nothing but 2 square into bracket n plus 1 plus 32 means it is 2 raised to 5 into x raised to 4 divided by n plus 1 into bracket n plus 2 so on, and let us call this as equation number 4. Since we also have a k equal to minus n, therefore by putting n equal to minus n, you will get another solution, that is y2 equal to a0 into x raised to minus n into bracket 1 minus x square by 2 square into minus n plus 1 plus x raised to 4 upon 2 raised to 5 into bracket minus n plus 1 into bracket minus n plus 2 so on. Call this as a equation number 5. The complete solution is obtained by taking the combination of these y1 and y2, that is y equal to a into y1 plus b into y2, where a and b are arbitrary constant. If we take a naught equal to 1 upon 2 raised to n into gamma n plus 1 in the solution 4 gives the Bessel functions of order n, and that is denoted by Jnx. So Jnx equal to a naught means it is 1 upon 2 raised to n into gamma n plus 1 into x raised to n into bracket 1 minus x by 2 whole square into 1 upon n plus 1 plus x by 2 raised to 4 into 1 upon 2 into bracket n plus 1 into n plus 2 etc. Or that is x raised to n upon 2 raised to n is x by 2 raised to n into bracket. We can write down this 1 as a minus 1 raised to 0 and to x by 2 raised to 0 in the divided by gamma n plus 1, because I will take this gamma n plus 1 inside the bracket, plus in the second term here minus sign is there, therefore we can take it as a minus 1 raised to 1 divided by n plus 1 into x by 2 raised to 2 into gamma n plus 1, plus second next term is positive, therefore we can take minus 1 raised to 2 divided by n plus 1 into n plus 2 into gamma n plus 2 into 2 into bracket x by 2 raised to 4 plus so on. That is x by 2 bracket raised to n into bracket minus 1 raised to 0 divided by gamma n plus 1 into, we can put this 1 as a 0 factorial into x by 2 raised to 0 plus minus 1 raised to 1 divided by gamma n plus 1 into gamma n plus 1 is gamma n plus 2. This is by recurrence formula of the gamma function into 1 factorial into x by 2 raised to 2 plus minus 1 raised to 2 divided by n plus 1 into n plus 2 into gamma n plus 2 is nothing but gamma n plus 3 into 2 can be written as a 2 factorial into bracket x by 2 raised to 4 plus so on. That means we are going to rewriting all the terms in that series in the some standard form, so that we can put it in the form of a series, that is x by 2 raised to n into bracket minus 1 raised to 0, minus 1 raised to 1, minus 1 raised to 2, in general minus 1 raised to r divided by gamma n plus r plus 1 into 0 factorial, 1 factorial, 2 factorial etc. r factorial into bracket x by 2 raised to 2r, because if you are observing the terms inside the bracket, you are having the terms involving integral powers of x by 2 to the power 2 into 0, 2 into 1, 2 into 4, 2 etc. x by 2 raised to 2r, or that is Jn of x equal to summation from r equal to 0 to infinity minus 1 raised to r divided by gamma n plus r plus 1 into r factorial into, I will take this x by 2 raised to n inside, so that it is x by 2 raised to n into x by 2 raised to n 2r becomes x by 2 raised to n plus 2r. This becomes the Bessel's function of first kind of order n, that is denoted by Jnx. Similarly, if you are replacing n as a minus n, you will get a j minus n x equal to summation r equal to 0 to infinity summation minus 1 raised to r divided by gamma minus n plus r plus 1 into r factorial into bracket x by 2 raised to minus n plus 2r. This is the series solution of the Bessel differential equation leading to that Bessel functions.